Okay, good morning. I hope everybody can hear me. Let's see. Yep, and that should be working. We're going to wrap up chapter 1 today and go ahead and start the chemistry chapter. And does anybody have any questions on anything before we get started? Okay. I'm going to go ahead and see if we can't get into chapter 1. Do a little bit of review here and then go on. Everybody should see the screen that shows the body cavities and the membranes. An exciting topic here. Okay, let's get out. Okay, body cavities and membranes. Why am I talking about this? Well, in lab last week, we got into the area of the small intestine and the lining of the small intestine, on the outside lining of the small intestine and the inside lining of the small intestine. And there are membranes that cover these areas, and all of our body, in fact, there are special types of membranes that cover the outside of the small intestine, that cover the inside of the small intestine, and there are two distinct types. It turns out all of our body cavities are lined with special types of membranes. The membranes are designed there to reduce friction because we don't like friction. Now, I think I said this last week, but in our bodies, we have two cavities, the dorsal cavity and the ventral cavity. And the dorsal cavity is everything in the back, while that is really only the brain and the spinal cord. We have the cranial cavity where the brain is, and the spinal cord where it is located in the spinal column, heavily protected by bone, the most protected portion of the body. In the ventral cavity, on the belly side, we have the thoracic cavity where the heart and lungs and the great vessels are located. And that's what the term for them, the great vessels. The great vessels are located, as well as the trachea and the esophagus. So those are located in the thoracic cavity, in the chest cavity. And then in the abdominal cavity, we've got the rest of the viscera, the stomach, the spleen, the gallbladder, the pancreas, the liver, the kidneys, the small intestine, the large intestine, the urinary bladder, reproductive organs, and internal reproductive organs in the female. This is what we find in the abdominal pelvic cavity. That's all the ventral side. Now, the thoracic cavity is pretty well protected. It's got ribs around the front and a sternum, and it's got the spinal column in the back. So we have a lot of protection for the heart and lungs in here. Not like we had with the brain and spinal cord, but then again, the heart and lungs have to move. The heart has to contract 70 times a minute. The lungs have to expand and relax 15 times a minute. So they have to move back and forth. They need a little more flexibility than just being held inside a fairly rigid structure. Again, this is what the body cavities look like. This is the breakout here in, they have it color-coded. The cranial cavity, of course, the brain, and the vertebral cavity, the spinal cord, that's the dorsal cavity, the back side, the dorsal surface. And then we have the ventral surface here on the right with the lungs. Each lung is in its own separate cavity. The lungs do not connect to each other. They connect to the trachea individually. So if something happened to one lung, the other lung is not affected or not directly affected. And they are in their own little cavities. They're called the pleural, P-L-E-U-R-A-L, pleural cavity. So we have each individual cavity for that. The heart sits inside its own cavity called the pericardial cavity, and it sits inside a sac inside there. And so it's protected too. It's protected by the sternum, it's protected by the ribs, the lungs are protected by the ribs and the sternum. The esophagus and trachea are protected, but they're all in separate compartments, separate subcavities within here. Now you get into the abdominal cavity below the diaphragm in this area right here, and you've got no protection whatsoever. You are going to be looking at fat and skin and membranes, and that's it. There is no protection. Below the ribs, all the viscera below the ribs only have soft tissue to protect them. When we get down into the pelvic cavity, we have some protection for the urinary bladder from the hip bones, but there isn't much protection there at all. And again, our dorsal body cavity protects the brain and spinal cord. The viscera. Now we use the term viscera for the heart and lungs and gallbladder and spleen. So we use the viscera for everything for internal organs, but we tend to refer to the viscera more just below the diaphragm. Even though the heart and lungs are part of that too, we tend to think of the viscera as the area below the diaphragm, but it really does include the heart and lungs too. They don't want to get left out. These cavities, as I said, we have the pleural cavities. Each cavity, when we have looking at the ventral body cavity, we're looking at the thoracic cavity. We have 3 locations. We have the 2 pleural cavities, one around each lung. If one lung is damaged or infected or inflamed, there's no reason to suspect that there would be an immediate impact on the other lung, unless the other lung is injured, or the infection spreads or something like that. Lots of people that suffer a blunt force trauma to the chest or a penetrating injury to the chest often have a collapsed lung. The other side is usually not affected. The mediastinum, which is the middle of the thoracic cavity, contains the pericardial cavity, and this is going to surround the great vessels and the trachea and the esophagus, but with the pericardial cavity itself only encloses the heart. So in this region in here, you're going to see the superior vena cava, the aorta, the pulmonary trunk. All these are the great vessels coming out of the heart. Plus you've got the esophagus and trachea right in here. But then the mediastinum, which is this whole area here, also has a cavity just for the heart, the pericardial cavity. I already mentioned all this. There's your ventral body cavity there. Now, I think we got to this, but it doesn't hurt to go over it again. Now, how do you designate the regions? How do you designate the regions of the ventral cavity, or the abdominal cavity, or what we also call the peritoneal cavity? The lining of the inner lining of the abdominal cavity is called the peritoneum. Well, there's 2 ways of doing this, and one of them is the simplest way, where you just divide the abdomen into 4 parts. Upper right, upper left, lower left, and you organize. Well, we have pain in the lower right side. We have a penetrating injury in the upper right side. That's pretty specific and pretty quick. A little more refined approach would be to take the regional view of the 9 distinct regions: the umbilical region in the front, in the center, the hypogastric and epigastric above and below, the umbilical, the right and left hypochondriac, the right and left lumbar, and the right and left iliac regions. So these are more specific but it may be, again, it's hard to challenge the benefit of grief, using the simpler approach. However, if you want to be very specific, pain, our pain is a good indicator that something's going on, and you want to try to be as precise as you can be when identifying where pain is coming from. However, our bodies don't play by the rules. Our bodies like to exhibit a phenomena known as referred pain, where pain shows up somewhere else instead of where it's supposed to. And if you've ever heard that individuals that have a heart attack or having a heart attack often have pain in their left arm. Now, your left arm has nothing to do with your heart at all. Why would you feel pain in the left arm? Well, it seems that the nerve that innervates a branch of the nerve that innervates the heart also follows the same pathways going to the brain as the nerves coming from the arm. And so pain signals coming from the heart are often interpreted from the brain as pain in the left arm. We also see that a person having a heart attack can have obviously chest pain, maybe, but sometimes they'll have a pain in their lower jaw on the left-hand side, because the nerve that does innervate the heart also innervates the lower jaw and the heart all the way down to the abdomen. So you could have a person having a heart attack and complaining of a massive, major toothache. Sometimes toothaches are just toothaches. So, and sometimes a left arm is just a sore left arm, and other times it's something else. Gallbladder. Gallbladder is located here in the right upper quadrant, a little green thing. You see there's the gallbladder. Gallbladder pain is supposed to be on the right side underneath the liver, because that's where the gallbladder lives. There's the liver there, and there's the gallbladder. But a lot of times people with gallbladder pain have it over their right shoulder, because again, our bodies don't play by the rules. Our bodies like to use referred pain. So sometimes these organizations, sometimes you can say, well, they've got a pain here on their side, on the right lumbar region, or the right still in the right upper quadrant, and it might be their appendix. So sometimes it's important to mark where your patient is experiencing the pain, even though that's not the real source. They're not going to know where the source is. They're just going to know they have pain. Okay. Lining these cavities, lining these body cavities. If the cavities are internal, they are lined with a membrane called serous membrane. If the cavity is internal, and that sort of meets the definition of a cavity, the internal lining of the cavity is called the serous membrane. Serous membrane cells look just like epithelial cells. They are probably stratified squamous. They are going to secrete a lot of fluid. They're going to have cells that look like goblet cells, only the fluid is serous fluid. We call these serous membranes. They are friction. They're there for friction fighting. The serous membranes are a double layer membrane that covers the surface, covers all surfaces in the ventral body cavity. So it lines the inside wall of the cavity. If you have the we have the parietal serous membranes, the parietal serosa. Now consider you have the chest cavity. Okay, you have the various cavities inside the chest. You have the pleural cavity, for example. That's where the lungs are located. Now, on the outer surface of the pleural cavity, you're going to have this Parietal Serosa. I'm sorry, on the outer surface of the, let me back up. The pleural cavity is a sac that's going to contain the lungs. Now, on the inside of the chest wall, there is a layer of what's called the Parietal Serosa. These are endothelial cells. They're not epithelial, they're endothelial because they're internal. They line the inside of the chest wall and they secrete fluid, serous fluid. If it were outside, it would be mucus, same stuff. So they secrete serous fluid. That is the Parietal Serosa, and it lines the inside of the cavity wall. So like the inside of the chest wall is lined with this. Now the cavity itself, the inner lining of the cavity, the viscera are covered with what's known as Visceral Serosa. They have serous membranes on the individual organs. So sitting on the surface of the lung, you've got the Visceral Serosa. So you have the parietal layer and the visceral layer, and in between is this serous fluid. It's like a jelly sandwich. You have the two layers of tissue, and you have this fluid in between, and that lubricates the movement. So imagine a jelly sandwich. You know, the two pieces of bread, if you can imagine a jelly sandwich, the two pieces of bread will slide back and forth across the jelly. Not so much peanut butter, because peanut butter doesn't want to give too much, but jelly. The jelly is slippery, and so the bread, slices of bread, are going to slide back and forth across the jelly. The jelly is the serous fluid. The bread represents the two layers of membranes, and so these membranes secrete that fluid, and now we have give. If the lung is sitting inside a parietal cavity, and it has a visceral membrane on the lung and a parietal membrane above it, and it generates fluid, then the lung can expand and contract without friction. So this is a double layer. Both layers, the parietal layer and the visceral layer, secrete this fluid. We have a double layer here, and in that gap in between, we get this fluid, fills up the space, and it's a lubricant. It reduces the friction, because our bodies do not like friction. If you think friction doesn't matter, rub your hands together for a few seconds and see how warm they get. Just 2 or 3 seconds and the skin's very warm. So we have this, for example. Here is the pericardial cavity surrounding the heart. We have the visceral pericardium on the surface of the heart. This layer here is what we call the parietal pericardium, and we have serous fluid in between. So we don't want friction when the heart's contracting. Here in the lungs, we have the visceral pleura right here, this blue band here on the surface of the lung, stuck to the surface of the lung. We have this parietal pleura stuck to the inside lining of the chest membrane, chest wall. And in this gap, the pleural space is filled with serous fluid. Same thing applies in the abdomen. We have a visceral layer called the Visceral Peritoneum on the surface of every organ in the abdominal cavity. And we have a lining on the wall of the abdominal wall called the Parietal Peritoneum. Again, we lubricate every organ. You know, our organs move, our stomach churns, our small intestine expands and contracts, gas develops, and food gets pushed through there. The same with the large intestine. Our bladder expands and contracts. So there's a lot of movement going on here, and we don't want to have any kind of friction. We don't like friction at all. And so we lubricate each individual organ with these serous fluids. Now, this is all on the outside surface of these organs. Now, if the organ is a hollow organ, like the small intestine is, then we have mucous membrane inside the organ. Why inside? Well, it's because the entire digestive system is open to the outside. From the mouth to the anus, it is one 30-foot long open tube. So here our lubrication is produced by epithelial cells, and they generate mucus. So internal, not exposed to the outside, it's serous membrane. Exposed to the outside, it is mucous membrane. Essentially the same types of cells and the same type of fluid that we see here, but it does the same role to fight friction. So every time, the internal components of our abdominal cavity move around, excuse me. Okay. So we don't like friction. And when our internal organs are moving around, which they do, we have to lubricate because we just don't like friction. To give you an idea of what a serous membrane looks like, this example here, imagine if you had a balloon that was big enough and only partially inflated that you could push your hand down into the middle of the balloon and you would have two layers form. Now, I'll tell you, this has never worked, but it's a good illustration. Even though every time I try it, I pop the balloon. Anyway, if you take a balloon and push down in the middle of the balloon, you end up with two layers. The layer that's up against your skin and the layer that's outside the edge of the balloon. That's what kind of layers we're talking about. That's what kind of layers we're talking about. An outer layer and an inner layer with a space in between. Now, these spaces can be ruptured. These spaces, in reality, these spaces can be ruptured or inflamed or irritated or penetrated. The pericardium, the sac that surrounds the heart, can be penetrated, and blood can fill up that space, and that's never a good thing. In the lungs, the pleural space can be exposed to the outside, and we can develop a condition also known as pleurisy. So there's a lot of things that can go wrong. 99% or more percent of the time, everything works fine. It's actually probably 99.99% of the time, everything works fine. But things can go wrong with these spaces and these membranes. So, okay, now let's get out of this and go into chemistry. So that's the end of chapter 1, as far as we're concerned, as far as the introductory chapter goes. So now let me go into chemistry. Here we go. Okay, everybody should see the screen that says chapter 2, the chemical level of organization. So it didn't work. Let's try it again. Interesting. Good. Let's try this again. Sorry about that. I thought I had it set up for us. No, it shouldn't work. Oh, understood about computers. Computers do all sorts of things that we don't want them to do. So let us let's try this again. And okay, well, maybe we can see it now. Okay, you should. No, it's not. Sorry, let's see this. Here we go. Let's try this. Okay, everybody should see the screen that says now chemical level of organization. Let's see if it's going to continue to work. And there we go. Okay, finally, everybody should see this. So, why in the world are we looking at chemistry in an anatomy course? You know, I'm not going to teach you, how to be a chemist. I'm not a chemistry major. I had no desire to be a chemistry major. I don't want to be a chemistry professor. However, the reason we talk about chemistry in the human body is because we have a constant series of chemical reactions going on in our bodies. We have to understand those chemical reactions. In healthcare, our bodies do things and respond to things based on chemistry. I've said several times, and I'm going to keep saying it, the reason that we breathe fast after exercise is not to get more oxygen, but to get rid of carbon dioxide. And the way our bodies monitor carbon dioxide is to measure the increase in the acid level in our bodies. Now, where does the acid come from? Well, when we breathe, when we exercise, we burn up sugars, basically. We get our energy from carbohydrates. So when we exercise, we burn up those carbohydrates, and in doing so, we release carbon dioxide. Anytime that you burn anything, you're going to release carbon dioxide. Anything based with carbon, any kind of fuel that you eat, or any kind of fuel that you use, like wood, or gasoline, or diesel, they all have carbon. And one of the byproducts of burning that fuel is going to be carbon dioxide. Carbon dioxide goes in the body, is produced, it goes into our blood to be transported to the lungs. It also forms something known as carbonic acid. It combines with the water in our plasma and forms carbonic acid. That's a chemical reaction. And the carbonic acid lowers, it increases the concentration of acid in our blood, lowers our blood, what we call our blood pH, which is a measure of acid and base in our blood. Our brain doesn't have to worry about the CO2 levels. It only has to measure, it doesn't have to worry about how many acids are around. It just monitors pH. And if our pH drops because our acids are going up, because it's sort of counterintuitive, the more acid you get, the lower your pH gets. If our pH drops, our brain says, hey, we got too much CO2. We got to breathe faster. That was a pretty convoluted, complicated answer, but to cover everything, we breathe faster after exercise to get rid of CO2 because of a chemical reaction in our blood forming more carbonic acid. So That's one of the reasons why we pay attention to chemistry. Now, when we look at chemistry, a couple terms we have to understand here. We have to look at matter and energy. Now, matter, as it says here, is anything that has mass and takes up space. Anything that has mass and takes up space. We can see matter, we can smell matter, we can feel matter. You know, matter is solid, matter is a liquid, matter is a gas. Matter has weight when it's exposed to gravity. Mass and gravity gives you weight. If you, what you weigh here on Earth is negated, is eliminated in space. If you were to go to the space station or go into orbit, maybe you got a ride on SpaceX, or maybe you know, who is it, Jeff Bezos or Elon Musk, or any of those, or even you know, Virgin Galactic. If you went into space with one of them or with NASA, you would be in orbit. You would be essentially weightless, but you would still have your mass. Weight is nothing, is mass plus gravity. Mass doesn't change. Your body mass on Earth is going to be the same on the moon. It's going to be the same in the space station. It's going to be the same in orbit. You still have that mass. Just eliminate the forces of gravity. Now, regardless of what kind of mass it is, you know, matter, as I said, can show up in 3 different categories, 3 different states. You know, when you go into space, you know, you have your body mass. Well, you know, our body mass is made up of solids and liquids and gases. We have all 3 forms of matter. Anything that's solid has a, you know, a definite shape and volume. You know, our shape doesn't change if we go into space. You know, our shape stays just the way it is. We have a head and arms and legs and feet and so on. That doesn't change at all. We have a definite shape. We have a definite volume. We take up a certain amount of space. Volume means we take up space. You know, if you're in a space station and you've got 160 pounds of mass, you're still going to take up space in that station. You know, that you're not invisible. So solids, you know, a definite shape and volume. You know, you pack things away in a box to ship it out. You try to fit everything into the box. You know, everything has a definite shape and volume. It takes up space. You know, you're packing for a vacation and you realize that, you know, you've got the contents of your trunk. Your trunk size is 2 trunk sizes too small to fit everything you want to take. Okay, because of the shape and volume. Now, the shape's not going to change. Your suitcase isn't going to change its shape. Well, okay, maybe a soft side could a little bit, but the volume's still going to be the same. Now, liquids are different. Liquids have a definite volume. A gallon of milk or a 2-liter bottle of Coke, 2 liters of Coke, that volume is not going to change. If the bottle is unopened, 2-liter bottle of Coke is still going to be 2 liters, no matter what you do to it, no matter what kind of shape you put it into. You may transfer that to you know, right now you got it you buy it in the Coke bottle, and maybe you transfer it to a 2-liter flat container to pack it easier. It's still 2 liters. The shape changes. The shape changes when you pour it into a glass. The shape changes when you drink it and swallow it. The shape changes when you knock the glass over and it spills out. But it's still the same volume. 2 liters on the floor is still 2 liters. The same 2 liters that was in the bottle is the same 2 liters on the floor, or the same 2 liters that you just consumed. You can't imagine drinking 2 liters all at once, but some people can. The point is that liquids have a changeable shape. their volume doesn't change. 1,000 milliliters of water in a beaker is 1,000 milliliters. Either you put it into a 1 liter beaker or a 10-liter beaker, a big, large beaker, or a cylinder or whatever. The volume isn't going to change. The shape will change, but the volume doesn't. Now, gases can change their shape and their volume. If you were to suck out all the air in the room you're in and compress it, it would still be oxygen. You were to suck out all the oxygen, not atmospheric air, but just suck out the oxygen, and compress it down, it would get cold, it would condense, it would become a solid, and it would be much smaller. And yet it's still the same amount of oxygen we started with. We compressed it and we formed it into a block of frozen oxygen. We call it liquid oxygen. It's almost solid, and it has a much smaller volume than it did before. The air molecules in our rooms, in our offices, you could suck them all together and create a vacuum. If the room could be sealed, you could create a vacuum and compress all the various gases and put them into small containers. The gases are still matter, but their shape has changed and their volume has changed. Conversely, you could take a tank of compressed oxygen, open the valve on the tank, and release that into the air around you. In the tank you have compressed oxygen. You release the gas, and it spreads out. Its shape changes, and the volume of gas in the room changes. So you can, matter is changeable. We can see it. We can see food. We can see solid objects in front of us. We can smell gases. We can smell odors. We can feel objects. We can feel rough objects and smooth objects. We can feel liquids. We have a hard time feeling the gases in the room, but on the other hand, if you start compressing your hands, trying to push your hands together, you're actually compressing some of the air between your hands, and so you can at least feel the pressure of the gases in the air as you're trying to push back. As we we're going to go through experience some lower atmospheric pressures over the next couple of days as the tropical storm winds itself over top of us. And the speculation is, are we going to feel the change in low pressure, the change in pressure from a higher pressure to a lower pressure? It is always been sort of I don't know if it's an urban legend or an old wives' tale, but many people believe that when the air pressure gets low, we have more aches and pains in our joints. And whether it's psychological or whether there's some basis in fact to that, we can experience this change in barometric pressure. That's air pressure. So are people going to be hurting more the next couple of days? So we can still feel the gases. Now, energy, so we got matter pretty well nailed down. We know what matter is. Energy is the ability to work, to manipulate your environment, to get matter to move, to do something with it. If you put fuel in your gas tank, you can drive. You've placed matter in your vehicle, in liquid gasoline or diesel in its liquid form. You place that in the gas tank, and now you can use that fuel to do something. You move your vehicle. You've made the matter move. You have manipulated your environment. On the other hand, you eat something. You eat something, and then you go cut the grass, or you work out, or you walk, or you run, or you work on the computer. All of that is using energy. So your work, to work, to manipulate your environment, to do things requires energy. We measure the capacity to do our work in terms of energy. If you charged your phone last night, or your computer, if your computer just died because the battery was out, computer doesn't work. Okay, it happens a lot. You go to do something, you pick up your computer, and it dies on you, or your phone. It has a little red bar that says you have 1% energy left. So you have to put energy back into your phone and computer. It doesn't work without energy. Now, the nice thing about energy, it doesn't take up any space. It doesn't have any mass. Your phone isn't any bigger than it was before when you charged it up. When you charge the battery in your phone or in your laptop, it doesn't change anything other than now the battery is fully charged. The amount when you put energy into a device, for example, nothing changes. Its mass doesn't change. Its size doesn't change. You just add energy to the device. And because energy doesn't have mass, energy doesn't take up any kind of space. Even the foods that we eat that we measure the energy content in the foods that we eat in the terms of calories. An apple has about 60 calories. A fruit bar has about 130 calories. A Pop-Tart has about 180 calories. We were at the drive-thru yesterday at Burger King, and I forget one of them. It's one of their jumbo burgers, 1,190 calories. That's simply a measure of the energy in your calories in themselves are not evil. They're not bad. They're just a measure of the available energy in that food item. That's all it is. The calories don't take up any space. The calories don't have any mass. It's just energy parked in a different version. Now, when we do work, we burn fuel, whether we're driving our car, whether we're driving our truck. We burn the fuel in the gas tank, in the fuel tank, the gas tank, whatever kind of truck we have or car we have. We're burning the fuel and releasing the energy in there. And if you drive really fast, you're it depends on. I don't want to say it that way. The faster you drive your car, depending on where you are, you may burn the fuel up faster. The slower you drive your car, you may burn up less fuel. But there's on the other hand, you get out on the interstate, you're going about, you're driving along at 80 miles an hour, 75 miles an hour, 70 miles, whatever you're doing, and you may discover that your car is more efficient. I'm not saying don't drive the interstate at 80 miles an hour, because that's, I'm not saying break the law. What I'm saying is that efficiency is different. We're not going to get into that. Generally, though, the more work we do, the more energy we burn up. You go work out, you go work around, cut the grass, and do stuff around the house that requires extra energy. You burn up, you use more energy to do that. You'll spend more energy if you were to hike up to Mount LeConte, you would spend more energy that than just a gentle walk around your neighborhood. Okay, what about energy? It's types. There's two types of energy: potential energy and kinetic energy. Potential energy is the old definition that still works: is energy at rest. It is stored energy. It's what you put in your phone or your laptop. It's what you put into your gas tank. It's what you eat. Potential energy, the calories in the food. You know, calories just represent the potential energy in the apple or the donut or the Pop-Tart or the Whopper. You know, calories just represent the potential energy. You charge your phone up, you eat a Whopper. You put gas in your gas tank, and you eat Coke. You drink Coke and have some fries. The calories and all that represent potential energy, stored energy. You're not going to eat a battery, but you're going to eat an apple, or you're going to eat a donut, or you're going to eat a Whopper, or you're going to eat a salad. You're going to, you know, there's all sorts of things that are going to have calories there. That is potential energy. That's inactive energy. Kinetic energy is when you use that and stored energy to do something. You know, if you are when you turn the ignition in your car starts. The energy stored in the gas, in the fuel in the gas tank, is now being released in the engine. You know, we carefully control the rate of fuel going into the engine, and the engine ignites the fuel, and it uses that fuel to make the engine turn over, and that makes the car or truck go. You know, so we take the stored energy in the gas tank, in the fuel, to make the vehicle go. We convert it to the potential energy into kinetic energy. And we go back, we do this all the time. We go from potential energy to kinetic energy. When we use our phone, we take the stored energy in the battery, the potential energy, and use it to light up our phone and let us get on Google and whatever else we're going to email and text and whatever else we do, all the things we use our smartphones for. That takes energy. We go from potential energy to kinetic energy every time. We use our laptops. Stored energy in the battery is potential energy. The laptop fired up with the display on the screen is kinetic energy. While it says energy in action, well, it's not really doing anything. We can still see and hear what's happening. So we go from potential energy to kinetic energy. Now, so we release that stored energy and things happen. Now, this animation here, which isn't the best, but what we're going to see here is an example of how we go between potential energy and kinetic energy. So this individual here has a bow and an arrow and a target. And they expect to hit a bullseye because they're standing 5 feet from the target. Even I can do this one. Right now, with the bow, with the arrow notched in the string, nothing is happening. The bowstring represents potential energy. If we apply energy to the bowstring, if we use our muscles to pull the bowstring back, we are using kinetic energy, and we are transferring that kinetic energy to the bowstring. When they release the bowstring, that potential energy in the bowstring will get transferred to the arrow and be instantly converted to kinetic energy. So we see potential energy in the arm muscles being converted to kinetic energy to pull the bowstring back. Moving the bowstring back essentially fills the bowstring with potential energy. It's at a higher tension. You let go of it, the potential energy in the bowstring is converted to kinetic energy. That's transferred to the arrow flies through the air and probably, maybe, hopefully, hits the target. Now, there's no sound on this. So potential energy is stored energy, kinetic energy is an action, energy of motion. We don't create energy, we don't destroy energy. Energy exists, it just exists in forms that sometimes we can't use. Now, the bow and arrow have low potential energy. The archer pulls the string back and puts potential energy in the string. I would argue that the arrow doesn't have, but now when you release the string, the potential energy in the bowstring is now given to the arrow. I don't think the arrow has any potential energy when it just split. Because if you've ever done this, you know that if the arrow slips off the notch and drops down, then it had no potential energy. Now, something else, though, that we see is that when we release the arrow also gets hot. It's going through the air, and pushing the air molecules aside creates friction. And you could measure the heat in the target, because when the arrow hits the target, not only does it punch a hole in the target, but if it was a paper target, you would see that the edges were slightly charred as the heat from the arrow going through the air is transferred to the target. Every time we go, because we're going from kinetic energy, and we're going from potential energy to kinetic energy, and we're getting hot, and we transfer that to the target. And every time we transfer energy, we give off some heat. Now, where did the energy come from in the muscles? Well, that came from the food that the individual ate. We'll get into more of this about that later on. Now, consider this. You go to Dollywood. Today's not a good day for Dollywood because of all the rain. However, you go on one of the rides. You go on the Eagle ride, for example, or one of the other coaster rides. And you know, going up the first hill, you know, the longer you go and the steeper the hill gets, the greater the ride down is going to be on the other side. As you go up the side, go up the first steep hill on the ride, you are putting potential energy into the coaster. You know, you're pushing that coaster up to the top of the hill. It has gained a tremendous amount of potential energy. And the only way to come back down, theoretically, is to go over the top and come down, because you'll notice that when we go over the top on that first hill on the left-hand side, our potential energy is quite high, and we convert that to kinetic energy. The potential energy and the kinetic energy tend to balance each other out. If you take into account the friction on both sides, the friction going up and the friction coming down, then it would be evenly balanced. The amount of energy going in and the amount of energy coming out, and taking into account a friction, it all equals out. Consider going into space. If you were to go into space, maybe you're going to the space station, maybe you're going to ride up on something better. You're going to go up in SpaceX, for example. The amount of energy spent to put you into orbit is, and you go to the space station, and then you come back. The amount of energy spent putting you up there is balanced by the energy that is given off when you re-enter. You know, space vehicles have heat shields so that they can go through the friction of the atmosphere. That return into the atmosphere, where the heat of the re-entry is dissipated, that balances the amount of energy spent to get you up there. You know, on the basis of physics, our universe likes to stay balanced. Okay, types of energy. Chemical energy, that's the big one for us. Chemical energy stored in the chemical bonds found in different substances, food substances, for example, other molecules, for example. Chemical energy. You see the calorie content of certain foods, that represents chemical energy. It's stored chemical energy from the chemical bonds holding the molecules of sugars and fats and even proteins together. You know, if an apple is 60 calories, or if a donut is 200 calories, or if a salad is 300 calories, and or slice of bread is 60 calories, 80 calories. You know, again, that's simply a measure of the energy stored in the chemical bonds of the molecules that make up the bread and make up the, the apple or whatever. Now, chemical energy is very important to us. Chemical energy is what we have in our batteries. We charge up our batteries in our phones, and there's a chemical reaction that takes place in our battery that allows us to store the electrical energy that's coming in. Electrical energy are charged particles, positive and negative charged particles. You plug something into the wall and you tap into that. You plug your charger into the wall and you charge your phone. Okay. We store electrical energy in the form of chemical energy in our batteries. But electrical energy is very, very important to us. Do you think that we're electric? Well, we are. We have a charge on every cell in the body. Muscle cells have a charge of minus 90 millivolts. That's their resting charge, minus 90 millivolts. It's measurable. Nerve cells have a charge at rest of minus 70 millivolts. And the movement of nerve impulses and the movement of muscles depends on these charges moving back and forth. So we are very much electrical. Mechanically, we manipulate our environment. We move matter all the time. We use our hands and our feet and our arms and our legs to do things. We work with our hands, we write with our hands, we use our keyboards, we run, we walk, we talk. That's mechanical. We pump blood. We expand and contract our lungs to move gases. We squeeze food through our digestive system and remove it. That is all mechanical energy, moving matter around in our bodies. Radiant energy, electromagnetic energy. Yeah, think about it. We have a constant body temperature of 98.6 degrees Fahrenheit or 37 degrees Celsius. We radiate heat. If you put 100 of your closest friends in a small room, it's going to get warm really fast because everybody's radiating out almost 100 degrees. And so that is radiant energy, heat energy. We depend on light energy to see. Light rays hit our eyeball and are focused on our retina and are turned into electrical charges, and then our brain tells us what we're seeing. So we depend on light energy for that. We depend on ultraviolet light, sunlight, to stimulate the production of vitamin D in our skin. So we are very, very dependent on radiant energy and electromagnetic energy in our bodies. We depend on that for a lot of things. Oh, and mechanical energy, sound waves. Sound waves are mechanical. They are pressure waves that move through the air and cause mechanical actions at our eardrum, at the bones of the middle ear, and they create vibrations in our inner ear, which are converted to electrical charges, so it tells us what we hear. So these, all four of these forms of energy right here, we use a lot. You know, these are all important to us. Now, one of the things that happens though with energy is we are always converting it from one form to another. We can't control that very well. If you turn on a light, as it says here, you go from electrical energy coming from the wall outlet or a battery powered light, doesn't matter, to light energy. If you have a flashlight on your phone, you turn the flashlight on, that's chemical energy being turned into electrical energy, being turned into light energy. You ever use your phone a lot to the point where it feels warm, where the phone is hot, or your laptop sitting on your lap, you realize this thing's hot. You know, a lot of times, because you know, with the laptop running on the battery, you're converting stored chemical energy into electrical energy, and there's a certain amount of heat given off. Usually when we convert from one form to another of energy, we give off heat. Your light bulb that's giving off light energy, you know, radiant energy, is also getting warm. You know, if you touch your light bulb, particularly the old ones, the ones before we had LED bulbs and stuff like that, the old bulbs would, you know, were painfully hot. You know, so every time we convert from one form to another, we are going to go, we're going to see a release of energy. The apple that you ate for breakfast this morning, or the bowl of cereal, or, you know, the fruit bar, or the Pop-Tart, or whatever you had for breakfast, maybe nothing. But if you ate something, the chemical energy in that food is going to be turned into mechanical energy for us to do things. But there will also be a certain amount of heat coming off. Heat energy is usually the energy that we can't use. It is the lost energy. Every time we convert energy from one form to another, some of that energy is converted to heat, and we can't access it anymore. We don't destroy energy, but we convert it. You know, as we go from one form to another, we lose some of that, the usefulness of that energy as heat. We can't recover it. So if you consider, if you have a fire pit and you put some logs in the fire and you light the logs and the logs burn, that's great. You know, what's burning, and well, I can complicate everything. What's burning is the stored fuel in the log, which in this case happens to be wood. Wood has stored energy. You know, wood is essentially mostly carbohydrates, mostly, you know, big sugar type molecules. Wood burns. It releases light. It releases heat. It gives off gases. And so you have a nice fire in your fire pit. You have the flames are coming up. It feels good. It looks good. You're comfortable with it. And you're warm when you get close to it. But if you step back about 10 or 15 feet from the fire, about maybe even 5 feet from the fire pit, you don't feel the heat anymore. Now, is that fire still giving off heat? Of course it is. If you were to get too close to it, you would definitely feel how hot the fire pit is. The heat coming off, you know, when you're burning a log, that's a chemical, that's a conversion from stored energy in the log to heat energy and light energy. Light energy spreads out pretty far. You can see pretty well the light from the fire there, but the heat spreads out rapidly. 5 feet from the fire, 5 feet from a fireplace, you don't feel the heat anymore. You know about a fireplace, you know, your front side stays warm and your back side stays cold. The energy is no longer usable. It's not destroyed. It just spreads out so rapidly, we can't use it anymore. Same thing happens in our bodies. When we eat foods that are high in calories, I don't want to say, let me rephrase that. When you eat foods that give you lots of energy, your muscles convert most of that into energy for them to use. Our muscles take up a lot of our energy because we have to do things, to pump blood, we have to breathe, we have to run, we have to walk, we have to push food through our digestive system. And so that energy is being used to power those muscles. But 60% of that energy radiates away as heat, and it's lost. We don't use it for anything. Now, our bodies are designed to use that heat to maintain all of our chemical reactions and maintain a constant body temperature. The reason that we have a constant body temperature is all that our bodies are used to running, our bodies are made to run at 98.6. And so we have a constant temperature, but that heat's coming off. We can't recover it. It's not destroyed, it just spreads out and spreads out. And until it's still there, it just is not in a usable form. So let's take a look. That's matter and energy. Again, calories are not inherently evil. You're not gonna walk by pick up a Snickers bar and hear it whispering in your ear, eating, because it's evil. Calories are calories. The calories from an apple are the same calories in a Snickers bar. They just represent the energy content of the food item. So if we are looking at chemistry, we've got to go into taking a look here at the elements that make up matter. Let's look at the elements here. Matter is made up of elements. Elements are simply any substance that can't be broken down into something simpler. For example, an element, let's take carbon. You can't break carbon down into something smaller than carbon, that's less than carbon. You can't take gold. Gold is an element. You can't break gold down into something that is less than gold. That if you have these parts, you can make gold. You can't do that with lead or hydrogen or helium or oxygen. Oxygen doesn't divide into anything smaller than oxygen. So all of these elements can't be broken down into something that is less than the element, smaller than the element. Gold, the element of gold will always be, it can't be anything simpler than gold, or simpler than carbon, or simpler than hydrogen. In our bodies, 96% of our bodies are made up of the big four: carbon, oxygen, hydrogen, and nitrogen. And 70% of that 70% of our body is water. So that's oxygen and hydrogen right there. Nitrogen shows up in the amino acids that make up our proteins and in our DNA. Carbon shows up everywhere in our cells. Carbon is in all of our fats and in all of our proteins and in all of our stored carbohydrates. So carbon is everywhere also. So 96% of our body are made up of these big four. The other, 9 elements make up 3.9% of the body. The most important ones of those would be sodium and potassium. And then there's a bunch of trace elements. Iron, for example. Got to have iron in our hemoglobin for us to carry oxygen in our red cells. All of these elements are listed in a table called the periodic table of the elements. And it is a mathematical progression. We don't need to go into any of that. But there's a sequence to the numbering of the elements, and the sequence of their appearance in the table. And this is what the table sort of looks like. It mostly looks like this. There's about 114 elements that are known. Element number 1 is hydrogen, right there. Element number 2 is helium. We've all had a helium balloon, and sometimes you know what helium is. Number 3 is lithium. Number 6 is carbon. Number 7 is nitrogen. Number 8 is oxygen. So hydrogen, carbon, nitrogen, and oxygen. The big 4 show up right here at the beginning. Hydrogen is number 1, carbon is number 6, nitrogen 7, oxygen is 8. We also pay attention to some of the lesser elements that we need a lot of are sodium, which is Na, potassium, and calcium. So these 3 right here are very, very important to us. We also have iron, Fe. Iron, again, necessary in red blood cells. So the common elements highlighted there in green. The big 4 plus, we got to use calcium, sodium, and potassium. I'll explain why the abbreviations don't seem to make any sense. Now, within these elements are made up of something called atoms. You've probably heard of atoms. You've probably studied atoms in school. Elements are made up of atoms, and the atoms are the smallest particles that still retain all the properties of that particular element. So an atom of gold is still going to melt at the same temperature that gold does. It's going to solidify at the same temperature that gold does. It would vaporize at the same temperature that a block of gold does. An atom of carbon has all the properties of carbon. An atom of oxygen has all the properties of oxygen. These atoms don't change. They have all the properties of that particular element. And the order of the atoms, the makeup of the atoms, is what we see giving these elements their unique properties. Why is gold shiny and durable? Why do we use gold in rings? Why do we use gold when we want to have important electrical connections? Why is gold plating or gold wiring or gold tips important in here? Is it conductive? Why do we use copper? What is the difference between copper and carbon? Why don't we use carbon wiring in our houses instead of copper? What is the difference? Every one of these elements on that table, their unique properties are caused by the makeup of and the structure of the atoms within the element. The atoms can be different. Now, every atom is going to have the same subatomic particles. Every atom is going to have protons, neutrons, and electrons. So the protons and neutrons and electrons are all identical. An electron from carbon is the same as an electron from oxygen, but it is the number of electrons and the number of protons and the number of neutrons, the number of the subatomic particles that give the individual element its unique property. If we look at a standard periodic table, above each element, if we look at a standard periodic table, we're going to have what's known as the atomic symbol. And that is the 1 or 2 letter abbreviation for the element. simple ones like O for oxygen, C for carbon, H for hydrogen, He for helium. It sort of makes sense. Helium, HELIUM, He. Those make sense. Some do and some don't. For example, let me go back here to the table. Here we go. Look at, there's carbon, N for nitrogen, O for oxygen, He for helium, Ne for neon, H for hydrogen, Li for lithium, Na for sodium. The Latin term for sodium is natrium. So the periodic table, when it was set up, used Latin terms too. And Na, or the term natrium for sodium has been around for hundreds of years. So the abbreviation for sodium became Na. K for potassium, directly underneath the Na. Kalium, Latin term for potassium. I don't know why, but Na and K. Ca is, you see directly next to the K, is for calcium. We use it all the time. Over here is Cu. That's copper. Sort of makes sense. But then you go directly underneath the copper and you have Ag. Ag is silver. Underneath the Ag, you have Au. And Au is gold. Some make sense and some don't make sense. Lead, for example, where is lead? Probably don't have, because this is, now, well, how about iron? Fe, ferrium for iron. Lead would be Pb. There it is. There's lead down here, Pb. Instead of Le or L, it's Pb for lead. Again, based on the Latin terms for a lot of this. The ones that we use the most, the ones that are the most important to us are going to be sodium and potassium, as well as the big four. Sodium and potassium and calcium. Calcium is easy to Ca makes sense. But I knew I get used to sodium and potassium, Na and K. Yeah. So as I said, atoms are made up of protons, neutrons, and electrons. They are subatomic particles. Protons always have a positive charge. You can't have a proton without the positive charge. Protons carry a weight of 1. It's an arbitrary weight assigned to it. So that just one proton weighs 1 watt. Well, it's called an atomic mass unit. Okay, so it weighs 1. But more importantly, a proton has a positive charge. Neutrons weigh the same as protons. They have a mass of 1, but they have no charge. Neutrons are neutral. And electrons have no mass. They're extraordinarily tiny, and yet their charge, they have a negative charge, and their charge balances the charge of the proton. In a stable atom, all of the protons are going to be balanced by the same number of electrons. If the atom has 6 protons, a stable atom will have 6 electrons. It isn't so much the size of the electron, it's the charge on the electron. So we have positive and negative charges. We have to, to be stable, we have to be balanced. And give you some examples here, and then we'll call it a day. Hydrogen has 1 proton. It has 1 electron. It doesn't have any neutrons, but it has 1 proton and 1 electron. Helium has 2 protons. It has 2 neutrons, and of course, it has to have 2 electrons. Protons and electrons have to be balanced. Lithium, 3 protons, 4 neutrons, 3 electrons. Neutrons don't play by the rules. Neutrons, that number can be variable, but they don't have any impact on the charge. The charge is, for an atom to be stable, it has to be balanced. So, okay, I'm going to stop us here. And unless anybody has any questions, I will post this today. I'll send you the link as soon as I post it. And you'll be able to go to YouTube and watch this and go from there. So lab this week is going to be wrapping up the second half of Unit 1. We're going to look at mitosis and cell division. We're going to look at the parts of the cell, and we're going to look at diffusion and osmosis. And I promise you it won't take as long as it did last week. So, okay, I'm going to get us out of here. Thank you for being here today, and I will see you all later.